And yeah, so it's joint work with Kevin Briggs and Carson and Zoe Niles. Yeah, so when I say that the groupoids and C-star algebras are built from local homeomorphisms, what I mean precisely is that they're built from something that we call a, not just us, but people call a Diacono-Renault system. Right, DR, which is the pair X, which is space, and sigma. Such that, so X is a locally compact Hausdorff space. And yeah, sigma is partially defined local homeomorphism. So, okay, we call the domain just dom sigma and the range sigma. So that is a local homeomorphism. And these sets, the domain and the range, are open subsets of your space X. And this is going to give us some sort of dynamics, and we can apply sigma over and over, but if it's partially defined, we'll have to kind of restrict the domain accordingly so that we can apply it over and over. So we'll write sigma n to mean sigma, and compositions of sigma, but like when we can. So n times where we're allowed, where it's defined. And but basically the idea of the project is this. You've got a Diacono-Renault system, and this allows you to build a groupoid, and like I'll show you precisely how it's built. You get a Diacono-Renault groupoid. And then you get C-star algebra from that. Right, groupoid C-star algebra. So Aidan was writing like a subscript R for the reduced C-star algebra. I'll leave that out because our groupoids are amenable, which means we don't need to worry about the norm. There's the full and the reduced norm are the same. And so yeah, Aidan was talking about how you can sometimes like recover the groupoid from the C-star algebra. What we want to do is try and see how much of this original system the groupoid or the C-star algebra kind of remember. So like, and we recover this. But it's not really like a reconstruction result in the sense that like we don't take the C-star algebra or the groupoid and then kind of build the action exactly. So it's more of a rigidity problem. So well, I don't know if this is what everybody means when they say rigidity, but I'll call it rigidity. So when you've got two such systems, you look at their associated groupoids or C-star algebras. Say the C-star algebras are isomorphic. Like, what does that tell you about the original systems? Or if the groupoids are isomorphic, what does that tell you about the original systems? Like, are they related in some way? And so we're going to see that we can't recover the systems exactly, like we can't say that they're exactly the same, but as long as our isomorphisms satisfy some certain properties, we'll get that they're equivalent up to conjugacy. So I'll write subscript conj. Okay, so just in words, all right, maybe horizontal. So we're going to recover pair to the notion of equivalence. I'm going to see. from its groupoid or C-star algebra. I'll mostly mention the groupoids and then bring up the C-star algebra at the end. But first I want to mention a few examples because we'll get some intuition from them, I guess. So by examples, I mean examples of Dirac-Monod systems, maybe you've seen before. Or maybe haven't. So the first is one-sided shifts of finite type. Got like sequences with letters, I guess, from some finite alphabet. Them all. This sort of system, and these have been studied a lot by Matsumoto, who had written a bunch of papers on this sort of topic for shifts of finite type around the time we were writing our paper. So we were quite inspired by his work, or like we cited it, and just mean inspired. The other thing that we kind of took inspiration from is graph algebras. So if you have a directed graph, so a collection of dots and arrows joining them together, or a topological graph, which we won't worry too much about, but if you've seen them before, I just thought I'd mention them. So this is where your vertex and edge sets have topologies and the operations are continuous. So a directed or a topological graph E, if you have such a thing, you can obtain a Dirac-Monod system in the following way. So for your X, okay, I'll start by saying this. So for your X, you take the path space, which for nice graphs, so we denote it like this, partial E. And for nice graphs, this is just the collection of infinite paths in the graph. And then, okay, maybe I'll write this and then I'll fill in some extra stuff. So then the sigma is the shift map that just chops an edge off. So if you've got like one edge and then a bunch more, just chop an edge off. So that. So X is the whole infinite head. I'm used to the other convention where it's a tail. And then in this case, the sigma is a local homeomorphism, but because we are working with partially defined local homeomorphisms, to get a proper sense of like to have this properly kind of give you an idea of what we're doing, I want my example to be a graph where there's boundary paths other than the infinite paths. So we're going to union on the finite paths, that's what this star means, that end at singular vertices. So what is a singular vertex? I didn't leave enough space. So, okay, I'll write it here. So, so this means, so partial E is the collection of all infinite paths, as I said, plus finite paths ending at sinks. So a sink is what it probably sounds like. So you've just got edges coming into a vertex, but none coming out. Or infinite emitters, which might not sound problematic because an infinite emitter is when so you've got your path and it ends at some vertex, and then that vertex emits infinitely many edges. Now you can follow all of these along like perhaps forever. So there might be a whole bunch of infinite paths here, but also when we talk about boundary paths, you're allowed to just stop at that vertex and that the path that ends there will be boundary path. Anyway, the point is that because we're throwing all of these paths in, we're in particular throwing in sinks themselves, like just as vertices, these are considered paths and paths that end at sinks. And so if you have just a vertex, you can't chop off the first edge because there isn't one. And so we update our shift map so that we're only looking at boundary paths of lengths greater than or equal to 1. And so now it's partially defined on our X. Okay. And then another example, I guess I'll write it up here, is when you've got some maybe a compact Hausdorff space or a liquid compact Hausdorff space, Canfield set, something like that. And sigma is a homeomorphism, and you get this sort of reversible dynamics. In this case, the groupoid is the transformation groupoid, which I went to find, but it's, well, I didn't define it, so thank you. So this is the transformation groupoid. Basically just mentioning this to connect it to things that people maybe. And then the Caesar algebra is the cross product. And these things are have been studied a lot with various people. And yeah, so that's all the examples I wanted to mention. Are there any questions, by the way? Yeah.
Convention are you using for path direction?
That convention. So yeah, so in the southern hemisphere, we usually draw our paths going the other way. And so then an infinite path would have like an infinite tail. But because all of my collaborators are from the northern hemisphere, going to perhaps thinks is a crime. But yeah. Anything else? Okay, so this thing is that I was going to define groupoids and then Aidan did it, but I had all these pictures drawn and I don't remember Aidan drawing pictures, so maybe that can be my new contribution. For those who haven't seen groupoids that much, maybe you appreciate a reminder. But yeah, I won't spend too much time on this. So a groupoid is a small category such that every morphism, maybe I should swap it. I think it's too high. Such that every morphism has a unique inverse gamma inverse. So you got gamma, how I picture it, and that's gamma inverse, and units here. So this is the source of gamma, and that's the range of gamma. And but yeah, there's a multiplication on your groupoid, and so the source is equal to gamma inverse composed with gamma, and the range is gamma composed with gamma inverse. And we read it's composition, so we read it like composition of functions from right to left. And composition, so composition of the pair is defined on this set G2 that I mentioned. So the source of alpha is the range of beta. And here's my picture of it. Here's alpha. There's the source of alpha. And then if it's equal to the range of some beta, you're allowed to compose them. And then that arrow is alpha beta. And the inverse is beta inverse, alpha inverse. And then the unit space is the collection of all the ranges, which is the same as all the sources. It's just all the dots. Okay, and then, wow, I'm writing really big and really messily. I'm sorry. And I don't know how to improve it, but I'll try. So
Big and messy is better than small and messy.
okay. Anyway, So yeah, so we give our groupoids topology as Aidan mentioned. And it's locally compact and Haskell. And then the multiplication and the inversion, what says operations, are continuous, and the range and the source, since they're defined in terms of those. Oh, and we call G et al. If its range map, or equivalently its source map, is a local homeomorphism. That's a for real local homeomorphism, not a partial. And okay, so now our reminder of what groupoids are. I'll show you how to build groupoid from a Dirac-Renault system, and it looks like the transformation groupoid that Aidan showed us. So our X here, that's the space, oh, the unit space, sorry. And then the sigma gets involved. So yeah, I said I was going to write DR. So for a Dirac-Renault system, X sigma, we define Gx, G subscript X, and this does depend on sigma, but I just don't write the sigma, to be the collection of triples, form. So here, the M and the N, the M and the N are natural numbers. And then X is something that can have sigma applied to it M times. So it's in X, but it's in the domain of sigma M. And Y is in the domain of sigma N. And then when you actually apply those two maps to X and Y, you get the same thing. Is that like what? Is that by right here? Is that fine? Yeah, okay. Okay, so unlike the ones Aidan was talking about, it's actually that's the curly brackets. I can't show it. Whatever. Unlike the ones Aidan was talking about, it's actually necessary to write the X and the Y, and that's because you have to apply the map to both X and Y to get them to be the same. So one of them doesn't give you all of the information about the other. So this is going to be a groupoid element. Think of as an arrow going this way. So Y is the source and X is the range. And then there's this integer that kind of keeps track of the M and the N to enough, like you don't need to keep track of the M and the N separately. It's enough to just have this integer here. So it's like a turtle with an integer in its shell. Oh yes, two operations. So that's the actual space. And then the operations are what Aidan wrote down before. So the multiplication, well, you're only allowed to multiply when the tail of the turtle is being touched by the head of the other turtle. And then the turtles like merge together. That's the multiplication, and then the inverse. Turtle turns around, and it also flips over. Turtle. No. Okay, and then when you work out the unit space, so like all the ranges can be worked out by just doing like gamma times gamma inverse, where gamma is one of these triples. You see that the unit space looks like all the triples of the form x0x. So this is why I just said before that the unit space is which is X, essentially. Oh yeah, and so I guess I meant homeomorphic, but I haven't said what the topology is. So the topology is generated by this basis sets. Basis of cylinder sets. So for open subsets of X and natural numbers M and N, we have these sets like this. So the notation is supposed to be kind of intuitive. So X is in U and Y is in V, and then the M and the N are satisfying these conditions over here. So yeah, so under all of that, GX is an amenable Hausdorff Natal groupoid, and I won't talk about amenability except to say that it means that there's no ambiguity when I say what norm we're putting on our C-star algebras. And it's second countable when X is second countable. Oh, and it's ample. Basis of compact open bisections when X is totally disconnected. Which in particular happens for directed graph algebras like a Diacono-Renaud. So for directed graphs, the direct Diacono-Renaud groupoid coming from those. Okay. So speaking of graphs, I wanted to revisit the example of graphs because I think I mentioned earlier, when I was talking about how this rigidity problem, I was saying like it's not going to be possible to recover the pair X sigma exactly. I mean, we know that X is the unit space, but it's not going to be possible to say exactly what sigma does. So to see why, we will look at graphs again. So going back to graphs. So when we have a graph E, and this gives us a Diacono-Renaud system of the boundary path space in the shift map. And so the groupoid, we usually denote it GE. This is called the boundary path groupoid, like just defined as I have already defined. And the groupoid C-star algebra is the graph algebra, so it's the same as the version defined using generators and relations. I think we've seen that before, for example, in the context of like Bickland's algebra. I think that's actually how graph algebras were originally defined. And this, yeah, I probably should have mentioned this earlier. So this condition down here in the context of graphs, when sigma is the shift map, this is saying that if X is a path and you shift off the first M edges, or I guess it's the last M edges, but anyway, the M edges on the left, and then do the same with the N edges of Y, then you have the same head. I'll draw a picture. So, so sigma NX equals sigma NY. This shift equivalence. So this is X. So there's like a bunch of different edges there. It is Y. So X goes by that point and Y goes by that point, and then they both have this same tail, head, I guess. So they're taken off like M edges of X, and then like N edges of Y. You get the same thing. So this is what I usually picture, and sometimes I accidentally use the word shift when I'm not really talking about shift maps. So if I do that, that's why. Maybe I can't believe I've already run out of boards. Aiden's talk was so nice. He just never ran out. Where is the here? Oh. So yeah, so I'll show you why can't recover X sigma exactly. So imagine that we didn't know that our sigma was the shift map and we wanted to try and work out what it was. Show you why you can't. Well, so yeah, here's why we can't recover X sigma from the X. So you might, I guess you might look at triples of this form, which are always in GX, because if you apply sigma once to this X, then you get the same thing. And then this number in the middle is supposed to be the difference between how many times you apply sigma, so 1 minus 0. So that's always in GX. So then in particular, if you consider the Diacono system coming from this graph E, so this is one edge E, another edge F, and then the boundary paths are just sequences of E's and F's, like infinite sequences. So then if I take X, so looking up here, if I take X to be F and F, and then E infinitely many times, and then sigma X, if it was a shift map, would just shift off one of the F's, have one in the middle. So that would be in my groupoid, which I'm now calling GE. Okay, so, but also, if I applied, so by sigma E, I mean the shift map. If I applied it twice to my X, then I would get E infinity, but E infinity is the same as shifting off an E of E infinity, because I've got infinitely many of them to spare. And so that tells you that F E infinity 2 minus 1, which is also 1, E infinity is in the group. Okay, so the problem is that you can't just say, oh, I'll just look for all the triples of the form X1, Y, and then I'll say that Y must be sigma of X, because as this example shows, like, you know, there's a question of like, what is sigma of FF E infinity? Like, is it F E infinity or is it E infinity? So yeah, so if we didn't know that for this GE, sigma was the sigma, we wouldn't be able to work that out. And so, yeah, the point is going to be that we can recover X sigma only up to conjugacy, which I'm about to define. The rest of the talk is about how to do that, recovering that up to conjugacy. Maybe I'll open ask for questions again. Okay. So definition. Two Diacono systems, X, and I'll call the sigma X, and Y, sigma Y, well, we say topologically conjugate in the paper, but because it's a topological property, but I won't keep writing it. So they're topologically conjugate if the spaces X and Y are homeomorphic. So if there exists a homeomorphism, which we're going to call it homeomorphism of conjugacy, if it sort of intertwines the sigmas. So, and also the domain of sigma X to map exactly onto the domain of sigma Y. Then H of sigma X of X needs to always be equal to sigma Y of HX. Okay, and then from that, you also get for free the other way around. So H inverse, but with a sigma y. Yeah. Okay, and this is an equivalence relation. So I'm going to write this squiggle conjugacy and their conjugate. And if they're conjugate, there's not necessarily a unique conjugacy, but there will be a conjugacy, like at least one. Okay. So okay, so now I want to put up theorem where we look at isomorphisms of the groupoids of like two conjugate systems. Sorry, isomorphisms of groupoids and that come from Diacono-Renaud systems, and look at when this, like what properties this isomorphism must satisfy in order to get that the Diacono-Renaud systems are conjugate. And the idea is going to be like, just like how the H kind of intertwines the conjugacies, we're going to have something that's going to intertwine the isomorphisms. So it's not going to be possible to just say, oh, two isomorphic groupoids must come from isomorphic or conjugate system. We need a little bit more. So we're going to have this thing that's going to be intertwined by the groupoid isomorphism, and I'm going to define that thing now. I'm going to define it for. Okay, I'm just going to stop rambling and just write because I'm going to write what I'm saying anyway. So let's say we have a locally compact Hausdorff abelian group gamma that separates the points for x and y. So I'll just say it's separating for x and y. We define precisely what we mean by that in the paper. But you should just think of gamma being R, the real numbers. It satisfies the definition. But it's sometimes nicer to think of it being the integers, which you can as long as x and y are totally disconnected, which they will be in the graph case. Yeah, graph case. So if they're totally disconnected, then gamma can be the integers. Okay. So now, given a continuous function from x to gamma, I'm going to define something called a continuous one cocycle, which is just a groupoid homomorphism, like a homomorphism, as long as the, you can only multiply 7 groupoid elements. That's what I mean. So, respecting that. So CF goes from GX to gamma. So we define it like this. So I plug in a triple XPY. So I'll define it with this limit, but the limit will just like mostly, like most of the terms will be 0. I'll be looking at the differences between all of the f of sigma x's and f of sigma y's. Okay, and the point is that if this is a groupoid element, at some point x and y have the same head in the graph setting, but at some point they're equal, right? And then the difference between these two terms would be the same, would be 0. And so therefore, this is just going to look like for whatever m minus n that can go in the middle here to make this going to look like just the difference between these two sums. And in the case where, so let's write it over here. If f is the function that just sends everything to 1, you get that this CF of xpy is just, I'll just say this thing equals n minus n. And so then you recover it's called the canonical cocycle. So we've got a generalization of that, and then we have this following theorem. So for countable Renault systems, x and y, x sigma x and y sigma y. The following are equivalent. So if your systems are equivalent, or conjugate, what does that tell you about the groupoids? Well, the groupoid's isomorphic, and the isomorphism is generated by a conjugacy. So in particular, there exists a conjugacy from x to y defining a groupoid isomorphism like this. So if you take triple xpy, you just use h to send the x and the y over to space y and keep the p the same. Okay. And okay, so that, I mean, 2 implies 1 is trivial, because if there exists a conjugacy, then the space is conjugate, the system's a conjugate. But we also have this third condition, that implies 1. Oh, and the proof of 1 implies 2 is reasonably straightforward, but the proof of the 3 that I'm about to write implies 1 is more complicated. So this one says that if you have a groupoid isomorphism, and you have a homeomorphism, so not necessarily conjugacy, otherwise we'd be done. Then what you need to check is that for all g, so continuous functions g from y to your group gamma, which you can just take gamma to be the real numbers, you just need to check that c of g, so defined like this, but this groupoid here would be gy, proposed with psi, which would then be a map on gx to gamma, is c of the function g composed with h, which is a continuous function on x. So then if that holds, then we showed that 3 implies 1. And yeah, so the proof is complicated in the sense that it uses a complicated paper, which I don't pretend to like completely understand all the details of. So the paper is, or Aidan is one of the authors. So Carlson, Sims and Tomford. I didn't write down the authors. Reconstruction of groupoids and C-star rigidity of dynamical systems. Yeah, and fortunately we had Toko working on this paper with us too, so he was able to help with the details of that. So anyway, so that's our groupoid results. And then do I have until, when do I have input?
Until 10:03.
Oh yeah, okay, that's fine. So I will, yeah, so I'll do the C stars part of the result. I've lost track of which board I should be rubbing out. Bottom one.
Can you say a word about the relationship between this result and other groupoid / full group reconstruction results? So there's this work of okay, who should I talk about? I guess I should first talk about Ruben and then possibly about Matsui. But then also Nicolas Matebon has something about this where they say that you can reconstruct certain. Well, I'm asking you, which what's the difference between what they do and this?
I'm not actually familiar with those results, although I did mean to say that like we were mostly inspired by graph algebra results for this. So there's a paper by Carlson and Rout from like 2017 on like eventual conjugacy, where they proved something like this in the graph setting, except they have these eventual conjugacies. So you have to apply sigma sometimes before you get the conjugacy, roughly speaking. And yeah, so there's a bunch of different graph algebra results that I have seen, but I don't really know what results. Like I'm not really.
There's a bunch of results in. Can I cite? I can cite Ruben. I can cite Matsui, possibly Nekrashevich, and Nicolas Matebon that talk about, you know, when you have topological full groups that come from certain groupoids and satisfying certain conditions, then the groupoids are conjugate if and only if the full groups are isomorphic, if and only if.
In what sense? Like, are they these kinds of groupoids that have a?
Well, I guess that's what I'm asking.
One thing maybe is that the groupoids that you work with will always be ample, right?
No, they're not.
And
Yeah,
it's
only
quite
if-
hard to define what you mean by a topological full group.
I mean, there is a definition though, so.
Well, outside of groupoids.
Yeah, it just might be very small. There might not be many elements.
Yeah, I think in this case,
Okay.
really be a boring thing. Yeah. What would
I mean,
you?
the X and the Y are often totally disconnected, and then
Yeah.
like they come from a graph, for example.
Yeah.
It's not like impossible to want to be ample at all, but
No, I know, but I guess
Okay, so this is for non-ample.
no,
Here you get
not
not necessarily
necessarily.
ample things.
Yes. Yeah,
Okay.
because all you have to do is take your X to be not totally disconnected, and then it's not ample.
Mm-hmm.
So there exist non-totally disconnected spaces, as you might know.
Yes.
I don't know if I'm answering the same question, but here the isomorphism of groupoids is somehow the weaker condition. It's a stronger condition that the actual shifts are conjugate, right? Like that's the groupoids could be isomorphic without the shifts being conjugates.
Yeah, like, I mean, you have to have this extra property, but I don't know what conjugacy of groupoids means, so does it mean?
Well,
isomorphism?
I'm not sure. There's some notion of isomorphism of groupoids in the appropriate sense.
Three is H and is H is the action of psi on the unit space or not? No, it's something different. H is something different. Within two, it is the action of.
Yeah, no, it doesn't have to be the same one, yeah. Although, this condition would hold if H was that. Okay, so the C-star algebras, so we saw the definition of a groupoid C-star algebra. I'll just write the C-star algebra of the groupoid is the closure of the continuous functions with complex support. We saw the operations, so Aidan mentioned. We have this involution product. And involution. That. I mean, this isn't just for GX, it's for Hausdorff groupoids in general. So now, to get a C-star result, we want something that's going to play the role of like this co-cycle in the C-star setting, the intertwined C-star isomorphism that will appear. So given gamma as before, and given a continuous function from X to gamma, we're going to define this action that will do the job. We just call this a weighted action. which we call gamma x, as in from x, and then the f after f, of the dual group. So gamma's a locally compact house of abelian group, so it has a dual group, and the action is defined like this. So if I have so pi character, and then I'll just say what it does to C sub C functions, and then just extends to the completion. Like that, and then evaluate it at a triple. I'll just call alpha rather than writing the whole triple in. So this just scales the function by, so you do chi, and then you need to plug in an element of gamma, and the element of gamma that you use is just CF, so you co-cycle from before evaluated at alpha. And if this looks familiar to you and you've done graph algebras, then I like done work with them, then I just wanted to confirm that when you have a graph E and the associated Diacono-Renault system, and when your gamma is integers, which is allowed to be for a graph because the boundary path space is totally disconnected. If you take F to be 1, then as we saw before, the CF of the triple just spits out the middle term. And then you see that this action is just the gauge action, the action of the circle, star of E. And this appears a fair bit in graph algebra literature. So we've generalized the gauge action. Okay, so I'll finish up by writing the theorem. Once again, say we've got two second countable systems. The reason for the second countability is just because it's a hypothesis of the did I write it down? There was this paper that I mentioned before. We used in the that paper as a second countability hypothesis. So, yeah. So rather than writing just equivalent statements, I'm going to separate out the two implications to kind of more clearly show the difference between them. So firstly, if we've got a conjugacy between the systems, so if H is a conjugacy, then we do get an isomorphism of the groupoid C-star algebras. That's nice. And it satisfies some nice properties as well. This one's 5. It is diagonal preserving. So that means that C0 of X, which sits inside the groupoid C-star algebra, it may or may not be a Cartan subalgebra. Just depends on properties of X and Y. I mean, the groupoid would need to be topologically principal or effective. And on like this level, the H, I mean, phi is implemented by H. So for all F and C0 of X. And we have the following condition. This intertwining thing. So if I have this action on C star of G Y that I compose with my phi, then that's the same as that's the same as if I take okay, if I take this, so we've got this intertwining thing happening, and this is So for all G from Y to gamma, and chi. So there's this condition, which I'm gonna call star. So then for the other direction, well, we were looking at paper by Matsumoto on shifts of finite type. And we were just trying to generalize his paper to, just more general Diacono-Renault systems. And in his paper, he has this result, and then he has the other direction being true. For us, we were able to, generalizing it, but also strengthen it in the sense that we don't need the diagonal preserving bit. So I'll just write up the statement and then I'll stop. So keep going a couple of minutes over time.
It's a y missing. Y equals y composed with that thing. They're both on the.
Yeah, sorry. Put that on my piece of paper and then oh, no, that is the right way around. Yeah, because the G goes from left. Oh, okay. Yeah, cool. Sorry. Okay, so now you've got star isomorphism and a homeomorphism from X to Y. That satisfies, so it's not necessarily a conjugacy, but it satisfies this condition that I called star. Then, so you get for free the diagonal preserving bit. And well, it's right in this order. And then you get that the spaces are conjugate, but the conjugacy might not be H. And then this conjugacy satisfies all of these properties, so such that that condition holds. And the condition star holds for H tilde. So yeah, it's a bit stronger because we dropped the diagonal preserving bit. And the proof uses the groupoid theorem that I wrote up before. And again, this CRST paper. And then in future work, we have, so I'll say coming soon. We have another paper with the additional co-author Jeroen Winkel, where we just restrict our attention to the Diacono-Renault systems coming from graphs, and then we characterize conjugacy in terms of the graphs themselves. So we have an algorithm for deciding conjugacy of directed graphs, deciding whether they're conjugate, and we show that you can perform a move called a generalized outsplit to both graphs, or if you can, then the graphs are conjugate and vice versa, to get like a mutual common graph. Yeah. That's gonna be soon.